Hello, everyone. Thank you for joining. So I will introduce Dr. Johannes Koeth. So we are honored to welcome Dr. Johannes Koeth as a physicist and expert in semiconductor laser technology with a PhD in physics from University of Würzburg. Dr. Koeth has been a forefront of semiconductor laser development using advanced materials like gas bar and gas. So during his PhD, he helped create some of the first laser in 1.5 and 2.0 micrometer range, DFB lasers, emitting laser diodes and bezels. Sorry. He also worked on DFB lasers for micrometer range. In 1998, he co-founded Nanoplus Nanosystems and Technologies GmbH. And Nanoplus has become a top provider of high precision lasers used in sensors, industry, and medical devices. So let's give a warm welcome to Dr. Johannes Koeth. So hello, over to you, Dr. Johannes Koeth.
Okay, thank you very much for this kind introduction.
Welcome.
Thank you very much for everybody who's here. And today I want to do a little bit about our semiconductor devices, I would call, or in general, and exploring a little bit their use in sensing applications. And I will give you a little bit of a mixture of device data, but I also show applications that are done by our customers a little bit as an inspiration for you to see what is possible with these kind of semiconductor devices I'm presenting here. So let's start off with a little bit of history. In 1998, as you just said, I founded Nanoplus together with my professor at the university at that time. And the starting point was a very new concept to make so-called DFB lasers. And these DFB lasers are single-mode lasers with very high spectral purity, which are perfectly suited for measurement tasks. So if you want to build an application where you want to measure gases, for example, these lasers are perfect. In 2001, we started here in our headquarter in Gabron, where I'm located at the moment, with the production of lasers. Since 2009, we have a second facility in Meiningen. And in 2017, we have a daughter company in the US, in Boulder, Colorado. And in 2020, I founded another company together with my professor at that time. It's so-called Semiconductor Technologies. I will briefly touch on this too later in the talk. Today, we are the leading manufacturers for lasers for sensing applications in the range from 760 nanometers, so very short, and up to 14 micron. We can provide any laser you need for your application. We are ISO certified, which is important for some, I would say, high quality applications in the safety area, explosion environments, for example, where you really need good quality of laser, good performance, and the documentation according to this. Yeah, this is our main product, not the fingers. This is my finger, that one here. And you see this little dust, more or less size particle on my finger. And if you put it under the microscope, you will see the structure you see in the picture down there. And let me start the laser pointer. Okay, now. And the main part of this chip here is just for handling the chip. The laser itself is just a small stripe down here. And here you have the contact pad that you can get the currents through the laser. And you have some contact metallization on top of the so-called ridge, which is here. And the structures giving the special properties to the laser are even smaller. You cannot see it with an optical microscopy. You would need an electron microscopy to see this grating structure, which is unique to our single-mode lasers and makes them so perfectly suited for sensing applications. Yeah, in 2023, we had our 25 years anniversary. So this is the most actual picture, most recent pictures we have from our staff. You can see a lot of people, 100 employees still at the moment at Nanoplus. And in this new company, Sensalight, we already have 45 employees, but on that a little later. Yeah, we have everything in-house. You can see some impressions from our clean room. Whenever things become really small, you need huge equipment to manufacture these devices. So you see, for example, in the left down corner, an electron beam system we use for writing these grating structures into a resist and then process it on from there. Yeah, we have all kind of back-end equipment to optical spectrum analyzers to characterize the spectrum properties of our lasers. This is how it looks like at the moment. So I'm sitting in this room at the moment, behind this window, more or less. This is our headquarters in Gerbrunn here in Germany. This is our second facility in mining, a little bit bigger. And in Boulder, Colorado, we have this nice 2 windows down here, not the whole building, just 2 windows down here, where we have office and a little bit of laboratory space for customer-specific requests. What is unique about nanoplus is that we are completely vertically integrated. And this is a very important point because we can really react very fast to customer requests. So we have all material design capabilities, all the programs, all the know-how, all the technology really to make a full design optimization, full simulation of thermal properties, of laser properties, everything. Then we have, at the beginning of the process, all the epitaxy in-house, at least for the most crucial, not so commonly available laser structures. And we have all the device processing, wet chemical etching, electron beam lithography, dry etching, coating, everything is in-house, and also quality control with electron microscopies, as you can see down here. And then you have all the device mounting. In the end, you don't want to sell a single chip, you want to sell something, a chip on a header. You can easily handle it and integrate it into your application. Also, we have also burn-in, where we use a robot. So the robot is here in the back. This is a lady from the back end, not the robot. The robot is really this here, the cabin, the cupboard, more or less. We have 5 main pillars of products. The first one are the so-called DFB lasers I mentioned before. They can cover the wavelength range from 760 nanometer up to 14 micron. And with this, we have different technologies, diode lasers, interband cascade lasers, and quantum cascade lasers. But we also have Fabry-Perot laser diodes, we have superluminescence diodes, we have mid-infrared lasers. And what is also very important, we do customer-specific technology development. So if you need a special package, a collimation, new technology, a new complete new device even, we can help you as long as it's in the semiconductor area. Limited to that. So starting off with our main product pillar today, the DFB semiconductor lasers. You can see here a simplified sketch of the laser. Here you have the laser ridge, and here you have these so-called grating bars, and the light waves of the laser travels back and forth between the front facet and the back facet, and couples a little bit into this grating structure of the laser. And this forces the laser really to emit only at one wavelength, one exact wavelength. Is coming out of our lasers with high spectral purity, so you have more or less no spontaneous emission in the spectrum left. It's really just one color. This is really what makes them so perfectly for this kind of application. So they have a large tuning coefficient, high power. We have different package options, so we can provide this thermoelectric cooler, for example, in this package, but also with a thermometer, an ATC in this case, measuring the temperature of the chips, that you can control the chip temperature very precise. You have some package with fiber coupling. You have smaller packages like this one here, and very small without a TC, or yeah, some more simple applications, I would say. As I mentioned before, we have different technologies really to provide different wavelengths of lasers. Here you can see a sketch of different laser wavelengths in the according technologies. So on the shorter wavelengths, up to 3 micron, we use diode lasers. Between 3 and 6 micron, we use so-called interband cascade lasers. And at the longer wavelengths, from 6 micron to 14 micron, we use QCLs, quantum cascade lasers. And besides these technology differences, we also have different material systems we can use. So at the short wavelengths range, we have the gallium arsenide family of material systems. When you come around 3 micron, we use gallium antimonide systems. Between 3 and 6 micron, we have this special gallium indium antimonide and then gallium indium arsenide antimonide structures, interband cascade lasers. And the phosphites we use for the QCLs, for the long wavelengths. Then we really want to get very long emission wavelengths. Here I brought you some examples of lasers we are using, we are selling. So for example, 760 nanometers, it's a short wavelength area of our window. They're normally used for oxygen sensing, because they're right above an oxygen absorption line. And you can see we have high side mode suppression ratio, one very pronounced, very clear peak. And then also we have low threshold current, a little bit above 10 milliamps. So it's really a very efficient device. And furthermore, you can tune the laser by tuning the current a little bit. So if you increase the current through the laser, it shifts a little bit to the red. And this can be used if you have an absorption line to tune always over this absorption line. This is a very important feature if you want to make a gas measurement or any kind of absorption measurement, because you want to probe the spectrum. And you want to see the zero lines to the left and the right of the absorption line, and then you can just tune a little bit through this absorption. Down below here, we have an example at 1877. 1877 is the wavelengths of choice for water vapor absorption. If you want to measure water vapor in some technical process, you would use an 1877 laser. Again, very nice properties. You can see it's below 10 milliamps, even very nice tuning capabilities. So it's a perfect device really to make a measurement of water vapor. Here, the first example, the NASA has chosen us to provide lasers for their space suits. And our lasers will be used to measure carbon dioxide and carbon monoxide and oxygen to ensure the quality of the ambient air in the spacesuit for the astronaut. This is a very nice application, and we're looking very much forward to provide these lasers for NASA. Now it's under development at the moment, but we are the laser manufacturer for these missions. And yeah, one day it will go to the moon again, hopefully, and later on perhaps even to Mars. I'm not sure. I don't want to go to Mars, I think, but yeah, for the astronauts who want to go to Mars, should have the perfect ambient air in the spacesuits, and that's the reason why our lasers are used for this application. This is another application. It's for an instrument called Neola. You can see it here on the right, and it's used to monitor the development of the lungs in preterm babies. If a baby comes too early out of the womb of the woman, the lungs are typically underdeveloped, and you want to measure and assess how the development of the lungs is moving forward. And for this, you shine a laser under the armpit into the chest, and then you detect on top of the preterm baby, on top of the chest, you measure the light coming out of the chest due to the laser emission. And this you can very precisely diagnose how the lungs developed, what is the status of the lungs, how is the oxygen saturation inside the lungs. And this improves the artificial breathing a lot for babies. So I think this is a very good, very nice application. And it was developed together with project partners like TTX Medical, NEO, and Lund University during a European project. Here, some examples of lasers at longer wavelengths, at 2.3 micron, for example. They're typically used for carbon monoxide measurement. You can see carbon monoxide up here. Again, very nice properties. You can see more or less as shorter wavelengths. And even at 3.34 micron, it's the typical wavelengths of choice. If you want to measure methane or ethane, for example, you have, again, still very nice properties. Former times, when only QCLs were around, it was very difficult to have a decent property at short wavelengths. But with our lasers now, it's possible really to have very nice performance at this long wavelength. And again, you can tune these lasers very nicely. You can see just with current, you can tune them more or less 8 micron wide, and then you can jump causally by changing the temperature of the laser chip to assess absorption lines more directly. Here I bring you an example of the use of our lasers in an application for in the farm, more or less, to measure plant-based food. The idea behind this Photon Food project, this was a European project, was really to measure wheat, nuts, and dried fruit to ensure that you have no fungal or mold contamination in your food. This is very important, especially with nuts, because you can have really toxic mold or mycotoxins in your fruits or nuts, and so it's really important to monitor it very precisely. And here are some examples of different mycotoxins. It's DON and OTA. You can see the absorption spectra down here. This blue one is DON, the green one is OTA, and here you see an LED we used for measurement. And this LED is done on an ATR crystal, and you bring the sample here into the window, and then you measure in the back here. And in this case, you use an array of diodes with filter, and with this you can measure the spectrum and can decide if your sample you put on top is contaminated with DON or OTA. We also have a laser-based system where we use a laser, several lasers which shine at different areas of the spectrum. Again, you see DON and OTA, and we have lasers at these points here. And with this, you probe the spectrum, and you can make a direct measurement. You don't need this diode array, and with this, you can again make more or less the same measurement, but much more compact. It's much easier. It's much faster, just by using lasers. Here I brought you a very classical example. It's a company called Spectrosensors. In former times, they have this very nice instrument here. And in this instrument, you can see we have a laser here on top. And this laser shines on a mirror down here. And here you have a detector. And what you do is you measure the remaining water vapor inside your natural gas. So if you have a pipeline with natural gas, you don't want to have water vapor inside, because water vapor and natural gas together form a very acid chemical which dissolves your pipeline, and then the pipeline blows up. And you have to avoid this. And for this reason, you have to measure very precisely the remaining water vapor in your pipeline. This is the measurement for it. It's a gold standard of measurement for this kind of application. And you suck a little bit out of the pipeline into in this pipe here. Later, you spit it out again. And yeah, in this very short bounce, you can measure very precisely the water vapor concentration. Sometimes you have a second channel here. This is this one here. This measures carbon dioxide. It's an additional marker for some chemicals. You can see these instruments are installed worldwide on very different locations. So this is here, for example, in an Arctic Circle, so very rough environment. Here you have it in the Mojave Desert, so it's very hot. So that is also the instrument has take care of a lot of thermal stress because of it. Here you have an instrument inside an explosion-proof package in an implosion-prone environment. Here you have some instruments inside a measurement shelter somewhere in Texas, for example. They are used quite commonly. Another example for use of our lasers in this very nice module where we combine 3 lasers into one laser beam is the so-called Passepartout project, where we measured NO, NO2, N2O, and N3, SO2, methane, carbon dioxide, carbon oxide, and carbon monoxide for environmental measurement. And we measure in 3 zones. So we measure on drones, we measure on top of buildings, and we measure on ground level in some shelters mounted somewhere, but also in cars. So sensors measure mounted in cars. And yeah, you can see the measurement set up as it was in the lab. We have so-called tuning fork access. I don't want to go into details, but anyways, we have here our laser shining the light into the measurement chamber. Below you have a power meter, and here you have a so-called tuning fork, and then you can test with different gases inside this chamber if everything works. So you just a current driver, a waveform generator, a lock-in amplifier. But we were able really to measure carbon dioxide very precisely. Here, this is a very interesting and very, how to say, relevant, at the moment, very relevant example. Lasers are used. It's about hydrogen measurement, hydrogen detection. As you know, especially in Germany, they dream of using hydrogen as one source for the energy grid. So we want to use hydrogen in our gas plants in future. I'm not so optimistic for the application overall, but anyways, you need to measure hydrogen also in other circumstances. And here you have some work from the Harbin Institute of Technology from China. They use our laser in a very unique setup, I would say. You have here the diode laser going through a long path cell, and you use a tuning fork in this case, again, for measurement. But what in this case, you measure more or less how you heat up the tuning fork with the laser. This is a relevant part. But looking at the results, it's very good results. You can really measure 45 ppm H2 as the lower detection limit. So it's for any area you have really to ensure that you don't get any explosion from hydrogen. This is a setup you can use because the detection limit is so low that you easily can have a warning very, very early. The measurement time was 1 second, and 2.1 micron laser was used for this measurement. Here's one of, I would say, I think one of the most important applications we are chasing at the moment, together with one of our customers. So the customer is Diamond Tech. You can see their logo here. I'm sorry, I forget to put it here in big, but they have developed this instrument, the so-called deep base, and it uses 8 QCLs in these 2 wavelengths windows here. so all over all 16 QCLs, and they measure glucose, blood glucose. And they developed this deep-based instrument, which already proves the technology in clinical environment. So they really have been successful with the clinical testing already. And yeah, you can see here the glucose level, and you can here see how the laser will probe the spectrum, and then you can later on decide how much glucose is inside. Our work here is to make the miniaturization in the next level, and so we do the laser, and we also do the miniaturization. It's one example of this technology branch we have inside our company. So we make this optical setup here with a lot of mechanical parts at the moment, which have to be aligned, and everything goes into this so-called deep pocket. And we hope that it will be the first commercial device later on where we really can make a blood glucose measurement at home, very flexible, on your way if you're on travel, very compact. So really like this technology. So the measurement scheme is a little bit surprising, and I will very briefly try to describe it to you. So here you have our laser, or two laser arrays to be precise. They shine the laser onto the lens, and the lens focuses the laser light onto the finger, and the finger is lying on nonlinear crystal. And this nonlinear crystal is nonlinear in the sense if you heat it up, it changes the geometry. So you shine the lasers into the finger one by one, and if blood glucose is present in a high concentration, the finger becomes warm, and this additional heat will also be transferred into the nonlinear crystal. And this nonlinear crystal will bend a little bit, just a very tiny little bit. And this bending is then probed with additional laser beam, where the displacement of the laser beam is measured. And the amount of displacement is a measure for the amount of heat generated in the finger. And the amount of heat generated in the finger is a direct measure for the blood glucose level in your blood. So it's a very indirect measure, but it works. And as I said, they very gladly also already managed the first clinical trials with this instrument. We hope that very soon we can go into a broader market with this instrument. So very briefly, I go through some more semiconductor devices. We have our Fabry Pro lasers, and we can even provide high powers with these kind of lasers. Again, we can offer, with our technology basis of diode lasers, interband cascade lasers, and quantum cascade lasers, different technologies and different wavelengths. We go up to 1 watt of output power. This is typical. The mounting we would use then, so-called rocket mount, so that you get the heat quite good sucked off of it. And because there is no wavelength selective element in it, you have this broad emission, very broad emission with single peaks inside of it, which are very small in themselves, but you have a lot of peaks side by side. We also provide packages with TC and NTC and everything you need to make a new application. Here's an example at 2.1 micron, and you can see up to 1 watt of output power. We have low power option, we have high power option. So the high power option really goes up to a watt, and the low power option is tens of milliwatt perhaps. Now let me very briefly show you the superluminescence diodes, these SLDs. We cover a range of 716 nanometer up to 3 micron at the moment with SLDs. They are broadband emitters. You can see a spectrum depicted here, so much broader than a Fabry Pro laser, and without individual peaks. It's really one giant peak, and it has use typically in measurement of liquids. If you want to characterize a liquid very precisely, you can use an SLD for this. Here, an example, you can see at 2.1 micron, we can extract 10 milliwatts of output power out of these devices. You see this broad emission here. And very typically, it's not a laser, so you have a round curve down here. But not as instant like in a laser. You just have a slow set-in of the emission of the power. And here I show you the mid-infrared LEDs. These mid-infrared LEDs can be ordered in a range from 2.8 micron up to 6.5 micron, and even longer. I show now an example, even longer wavelengths. They are true CW at room temperature, so this is really unique. We are the only ones who can provide this kind of mid-infrared LEDs. They have more than 2 milliwatts of output power, and they have this really broad, more Gaussian-shaped kind of emission, It's not perfectly Gaussian shaped, but it's a very broad emission. You can see a spectrum at 4 micron, 4.1 micron. In the corner here, you can see it's really, really broad. It has a line of 1 micron more or less, and 2 milliwatts of output power. We have customer-specific package for this, and we have improved the output power. Here's an example of a 9-stage LED, so in a structure more or less. It's 3.4 micron with 5 milliwatts of output power and 10 milliwatts of output power. So really can provide more power if needed. We can not only provide more power, we also can align these LEDs in an array. So in a 2-dimensional array, you can see here 1 million LEDs in an array. So it's a high pixel count. You see 4 arrays on a 3-inch wafer, and you can see here the individual pixels. And we always put 4 pixels together, and 4 pixels share one common contact in the middle. And what is important, at 77K, these pixels are designed to have a peak wavelength at 8 micron. You can see it here, 8 micron. It's the wavelength. And if you go to higher temperatures, close to room temperature, everything shifts out to 10 micron. So it's interesting array which is used in camera testing. So if you have an infrared camera, you want to test the camera. And the company CDS uses these arrays, our arrays, LED arrays, to make systems for testing of cameras. You can see here in the back is our LED array. This is the instrument made by Chip Design Systems. And this here is a very well-known company doing cameras, and you can test everything in the system setup. So the really nice thing about it is that you can go to really high speeds because the LEDs instantaneously switch on or off. So you can make a scene projection with really, really high speed. And this allows really to go to the extreme testing of these cameras, which is needed for especially for countermeasure applications. Now, let me switch over to the interband cascade infrared photodetectors. So we use the same scheme, more or less, we use the interband cascade lasers to make detectors. There are some adjustments because the challenge is a little bit different, but we have, again, a cascading scheme where we have an absorber structure, we have an electron barrier and a hole barrier, and we repeat this structure so they are cascaded and every carrier is recycled. And if we adjust the so-called indium arsenide layer, indium arsenide gallium antimonide superlattice, when we adjust the layer, we can address different sensitivities. So if we only have 5 nanometer layers, we go to sensitivity around 6 micron. If 6 nanometers, we a little bit below 8 micron, and 8 nanometers, we well above 8 micron. We can simulate everything. We can grow these things in our MPE systems. And here you can see the measurement results of one of such a photodiode. So it's in indium arsenide gallium antimonide super lattice absorber. You can see the structure depicted here. I don't want to go too much into details. You can see the X-ray of the structure. So you can judge from this that the quality, the close quality is very good. And here you can see the detectivity. The detectivity is 8 times 10 to the 8, so it's quite good compared to an MCT. And you can see the cut-off wavelength is a little bit above 6 micron for this kind of structure. So these are very nice detectors, very efficient. And if you compare to an MCT for this indium arsenide gallium antimonide superlattice, we have performance more or less like an MCT, but with the benefit that they are not, that you don't use mercury and all this toxic stuff. You just use gallium and indium and alunite, which are not toxic, which is important if you think of the European REACH agreement, where you have to very soon have to omit any toxic detectors. If we use a little bit different composition of the superlattice indium arsenide antimonide, we can perform with an MCT at 200. Our performance is as good at room temperature as an MCT at 230 Kelvin. And you can see we can go to longer wavelengths a little bit. So you have detectivity up to, I would say, 8 micron, a little bit below 8 micron. So these are very nice detectors, and I hope that they will be used a lot in applications. So as promised, I tell you a little bit about sensor light technologies. I showed you all these nice applications. Our lasers are used, or semiconductor devices are used in gas sensing. And if you look closely, you will find out that all these applications are low volume applications, going up to 1,000, perhaps 10,000 pieces a year. High quality, always a little bit different from customer to customer. And so I'm absolutely convinced that there are applications which would address mass markets. And mass markets, when you need millions of lasers, the lasers all have to be exactly the same. You have to provide really high volumes. And nanoplus is not set up really to provide these really high volumes, because we are more equipped to make individual lasers, one laser even per customer, up to 10,000 or perhaps 100,000 lasers, but not millions of lasers. And this is the reason why Alfred Feuchel, my partner, and I founded Sensor Light Technologies. You see, it's a new building here. This is our building. You have down here, you have the clean room. You have some office spaces above. So everything is in-house. And in principle, the products are exactly the same as for nanoplus. So you see down here our diode lasers, interband cascade lasers, quantum cascade lasers. We have here the Fabio Pros, SLDs, even technology developments they would do. And they have one unique device we don't sell here. These are these widely tunable lasers, where you can cover tuning ranges of 140 nanometers with one laser. This is unique to sensor light. But the difference is that they are equipped really with high volume equipment. So they cannot provide 10 lasers or 1 lasers or 100 lasers. They provide lasers when it comes to 100,000, 1 million, 2 million, 5 million. This is the aim of this company. And one very first application we are aiming at is the measurement of blood alcohol. So, especially in the US, for example, it's a problem that you have a lot of drunk drivers, and you want to really avoid accidents because of drunk drivers. Typically, in the US alone, 11,000 people die every year of drunk driving or caused by drunk driving accidents, and this is way too much. And so the idea is that we develop a technology where we can avoid drunk driving. And the idea is to put one of our nice lasers into a starter button of a car. So this should pick the starter button of the car. And whenever you press the starter button of the car, there's a short laser light illuminating your finger. And with this, the finger more or less glows, and you look then at the light coming back from your finger. And you use a broadly tunable laser so that you can probe the spectrum over a wide range of wavelengths. And I brought you here an example spectrum of alcohol in water, which is quite comparable to alcohol in blood. And you can see the alcohol spectrum in these oval-shaped blue things. And you can see it's a very tiny absorption peak only. It's really tiny absorption peak. And it's a 40%. Now, in addition, you have to shrink it down to 5 per mil in blood. So it's really much less. And so the signal will be much smaller. But still, you have to measure it. So you understand a little bit the challenge of this measurement. And we developed this system together with a consortium. It's called DATS, Driver Alcohol Detection System for Safety. And it's funded by the American government. And behind this, or inside this consortium, there are also all the auto manufacturers like Ford or Toyota or Mercedes-Benz, and Volkswagen is in there, Volvo, Porsche even. And they all push us to develop this sensor, this alcohol sensor for their cars, and hope really to get rid of all these fatal accidents which are caused by alcohol. Yeah, this was the overview I want to give you about our lasers, about applications, and the use of our lasers. Thank you very much for your attention, for your time you spent with me, and I'm open for your questions. Thank you very much.
Hello, participants. If anyone has any questions, please ask.
Johannes.
Yeah.
Yeah, that was a nice talk, Johannes. You covered so many things. I am a bit curious on one particular application I read in one of your articles on the superluminous diodes or LEDs. You also speak about something on the gyroscope application. So can you please share if you have any information about it, like gyroscopes imaging that becomes very good with the SLDs. Is there anything you can share on that, please?
Oh, I'm sorry, I cannot share too much on this application.
Okay.
But yeah, they are used in different kind of applications like gyroscopes. But also, I can share a little bit that they are also used in blood glucose measurement.
Okay.
But then for a sensor which is implanted inside of the body. So you put the sensor inside the body, and it's more or less important for diabetes 1, type 1, where you need a very close monitoring of your blood glucose. We have a partner in industry which successfully demonstrated also the blood glucose measurement with our SLDs.
Okay. Thank you. Thank you very much, Johannes.
You're very welcome.
Anyone else?
Feel free to ask me anything.
Yeah. From my side, are you providing the tunable laser only for that alcohols, that car application, or you are providing for gas sensing also?
So at the moment, these tunable lasers are under heavy development. In future, we will sell them also from nanoplus for individual customers. But at the moment, we really have tough fights to increase the yield to a level that it's sustainable. And this is the part we do at the moment in this project. I think we are on a good path. We know what to do next, and really can hopefully within this year improve it so far that we can, perhaps beginning of next year, provide these lasers even in individual sales to individual customers.
We have a question from Srijit in the chat box. The question is, what impact can oil have on the laser enhancement and application for medical and underwater communication?
So underwater communication, the lasers are used in underwater communication, but I really don't know too much about it, I have to admit. Not every customer is very open about the application details, so I cannot tell you too much about it. But in principle, yes, it's possible.
Okay, thank you. Anybody else has any question?
In NeoLens application, you're using LED or laser?
What kind of application? We don't know it.
You told NeoLens, right? That for the kids, you showed one application, right?
Yeah. So we have this one photon food application where we use LEDs as a broadband light source, and then we use later this filter array with photodiodes. This is the only application I know the details about. We have one customer using lots of application LEDs in a strange application, which seems to be related to some military things, but I don't know it. But yes, this photon food application is an application where I know the details.
Yeah, thank you.
Hello.
Hmm?
I have one question. So, how do you take care of long-term stability of the lasers which you use, like in terms of spectral purity and coherence? Do you have any feedback mechanisms in place to measure that in real time?
No, we don't have a feedback mechanism in place. That's a good question, definitely. This is done by our customers. Our lasers are very stable in long time, and it's a little bit of pity because we don't have a replacement business. So it's not happening, more or less. What our customers typically do when they want to really ensure that they track everything, they use the absorption line itself to reference the wavelengths. So, for example, if you want to measure water vapor, you normally always have water vapor present. And then this water vapor line is your reference point, because you know it's always at the same spot in the spectrum. And then you can more or less compensate for these very small aging effects you have over time. So over time, the wavelengths might shift. It's not necessarily so, might shift a little bit, and the threshold current might be a little lower or higher. But all overall, the lifetime of our lasers are amazingly high.
Thank you. I have one more follow-up question.
Yeah, sure.
Do you do any like Halt and Haas test in your laser system, like accelerator aging and all that?
Yeah, we do it once in a while at different wavelengths for different applications. We do accelerated lifetime tests on a regular basis. So sometimes just to check is everything still in place. For one application, the quantum cascade lasers, we even did very rigorous military testing of shock and vibration and humidity and temperature and everything else to ensure the performance of our lasers. And all of these tests we managed very brilliantly. Also for the space mission. So we have one laser already on Mars measuring the atmosphere of Mars. We have several lasers in space, in satellites for in the application where the Earth is measured, the troposphere is measured. So we have many lasers in space. So they are also a very good lifetime assessment was needed. Our lasers managed it perfectly.
Thank you.
You're welcome.
Thank you. We have one more question from Abin. The question is, did nanoplus has femtosecond laser for terahertz spectroscopy?
No, I'm sorry. No femtosecond lasers yet.
One more question is there. How do you take care of long-term stability of laser in terms on spectral purity? And do you have any feedback system in place?
So we don't have any problems long-term with spectral purity. So spectral purity is not an issue at all because the structure giving the spectral properties out of metal, and they are even covered with some insulators, so they are very, very stable in this laser matrix. And again, I said before in this example with the power and everything, this again will be referenced by our customers normally, or monitored by our customers normally by measuring the absorption line of the gas here. Sometimes they even use an absorption line close by as an additional reference, so even from another molecule, to really ensure the overall performance of the laser.
Thank you.
You're welcome.
If anybody have any questions, they can directly mail us on ls_marketing@laserscience.in. I will forward it with the Dr. Johannes, and you will get your answers.
Yeah, definitely.
Yeah. So thank you everyone for joining. Thank you, Johannes. Thank you, Daniel.
Thank you everybody for being here. Thank you very much.
Thank you very much.
Thank you.
Thank you.
Bye bye. Have a nice day.